All right. So we're talking about linear approximations in calculus here, and I want to start with a line, and I want to start with the forms of a line that you've learned in previous math classes. So take down as much of these notes as you can as I go through them. So most of these are pre-filled. So if you watch this video later, you can just kind of see what we've done all at once. So consider the function y equals 2x plus 1. All right, so this is our first function here, and that is a straight line, as you know, and it is drawn on the graph over here to the right. Okay, so it's got a slope of 2, and it's got a y-intercept of positive 1. And so here's our y-intercept, and then the slope rises a rise of 2 and a run of 1. Okay, positive 2, positive 1. All right, so this is in the form of y equals mx plus b. Well, we can change this form. This is the slope-intercept form. We can change this around a little bit, write it as y equals b plus mx, and then it starts to look a little bit like, if you notice, it starts to look a little bit like the point slope form. Okay, so I'm going to take the b over to this side. I'm going to let this x part be x minus 0. And then what you have is y minus b, which b is a y value there. And m is still the slope, x, and 0 is the x value for a point. And that looks an awful lot like the point slope form of a line. Okay? So those two, they are related somewhat, yes. But the point of this is that we can use a point on the line, and we can use the slope of a line to determine values of another point. All right? So over here on the right, I have my y-intercept of 0, 1. I know my slope of 2, and so it's going to be easy for me to calculate what this missing y value is over here on the right. Okay? So using a slight variation of the point slope form of a line, we can predict a y value on the line given another point and the slope. All right, so we have been doing this before, right? We've generated equations for lines using the point slope form. But if you think about it, if we have, if we're given an x value, like I'm given over here, x equals 1, I'm given at another point, and I know the slope, m equals 2, then I can fill in all of the values except for one value, and that would be this y2 right here. I can fill in all the values except for that one, and I can solve for that y value. Okay? I've got a little note over here. Okay? So let me just, this is supposed to be shrunk down a little bit. Give me 1 second. Okay. All right. So yeah, if you think about this, this here, when x1, y1 is this point that's given 0, 1. So here's x1 in our slope form, and here's y1 in our slope form. When that is given, okay, I'm going to take this y1 over the other side. So this is given, this x1 is given. And if I'm given a second x point, this is given, and the slope of the line, this is given, then you see it's easy for me to solve for y, right? Okay. Now that's not too hard to understand, but that leads us into our, this is the basis of our concept for today. Okay, so in this example on the right, we can use this form of a line to solve for the missing y value. Okay? All right. So let's do that. Let's do that. And so let's say y2 I don't know, but y1 was this value of 1, and the slope of the line is 2, and x2 minus x1, so x2 is 1, and x1 is 0. So the second y value is 1 plus 2, y2 equals 3. So this is the y value when x equals 1. Okay, so if we go back up to this graph up here, then when x equals 1, y equals 3. So this is the 3 value there, okay? Right here. So what have we done? And again, this is gonna seem like not calculus. Like this is not calculus. This is basic. This is pre-calculus stuff. But what's very important is that this right here is super important, because this is the equation that we're going to be using today. It's just going to look a little bit different. Okay. So we are going to be finding a y value on a straight line. Okay, today, and we're going to be filling in all the rest of these values. So here's the point of this lesson, okay? We're getting to it now. This can be used as a good approximation for curved graphs too. So right now, obviously, we used a straight line, right? We were looking at a straight line here, and I predicted this y value for this point. But what we can do is we can use this same concept to predict a y value for a value on a curved line as well. So let's just read this here. So this can be used for a good approximation for values on curved graphs too. As long as the x values are close together, you can approximate a value of the curved function using the linear approximated value. This is the essence of linear approximation. Okay, so let me just pause on this graph for a little while. Now notice that the red graph, okay, this looks somewhat like a radical function or root x or whatever it is, but it's a curve. Okay, so this is a curved graph. If we have a tangent line, and we know a lot about tangent lines, right? We've been studying tangent lines for a lot. We got a derivative there, an equation of a tangent line. We've talked about that all throughout calculus so far. So if we were able to identify a tangent line, what is really neat is that if you zoom in to the curved red graph, if you zoom in incredibly, like zoom, 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 what you'll find is that the red graph, as curved as it might be, if you zoom in, the smallest little part of it appears linear. Okay, and that's really important. Now it does start to deviate, but look at, if we have x values that are focused right in here, from here, to here, check this out. On this graph itself, this is a full 0.8 units. It's almost one full unit. This is 2, 4, 6, 8 units, 0.8 units. And the line is almost identical throughout that span. Now, obviously, if we zoomed in, there would be a difference, right? A tangent line technically only touches a curved line at one single point, but it's very, very close. The thickness of the line on Desmos here, you can't even tell the difference. You see that? The red line is totally absorbed by the straight blue line, or the red curve. So there is a concept called local linearity. Now, you know what local means. Local means very close to us in a certain region, right? Values that are very close to one another. They locally occur. And linear is straight line. So local linearity for any curve, if you zoom in far enough, the curve will look like a straight line around a certain point. Right? And I can zoom in on any part of this graph, and the more I zoom in, the more this curved graph, the more it will straighten out. This is what it'll look like if you zoom in. It just kind of straightens out as you zoom into a point. So this means that the function f of x, whatever it is, in this case it looks like it's a radical function, but even if it's a parabola, or we've got a sine graph, or anything like that, as sharp as you want to make it, as sharply curved as you want to make it, if you zoom in far enough, the graph itself in a very small local area will mimic its tangent line. Okay? Won't be identical, but it'd be super close. Like we're talking 10,000ths of a unit maybe, right? So super close. But it'll be a very good approximation. So this means that the function will approximately mimic its tangent line immediately surrounding the point of tangency, which I've tried to show you right here. Now, if you zoomed into 0.08 units, right, then it's virtually the same. And even farther than that, it's almost identical. It isn't identical, but it's pretty much identical. So, given this fact, the concept of local linearity, what we can do is we do not have to know what the function really is. We don't have to know what the function is. All we need to know is we need to know what this point of tangency is on the function. So we need one point. And if we can find the slope of the tangent line, whatever that slope is, I can then use that slope and I can just barely inch over a little bit and I can approximate where that graph is going to be. Okay? So think about this example down here. Okay, so here's a graph, and I've drawn the red graph. But let's say I didn't know what that red graph was. Okay, all I knew was that I had a point that's on the graph somewhere. And if I told you that the slope of the tangent line looked like this, then you would be able to tell me that this graph is looking maybe like this, right? Or it's looking like, oh, actually I should leave that there. Let me just draw that again. Oh, that's better. It's looking like this, or it's looking like this, right? Or it's looking like this, right? Or, I mean, I'll do one more just to, I know it's getting busy here, but it could be like this, then cross over. So any of these. But my point is, if you zoom in, like I'm going to actually zoom in on all this, notice that all of these graphs that I drew, let's see if I can do this in yellow. Here's the point of tangency. All of the graphs that I drew in this little area, they're all in this little circle. You see, the graphs are all in there. So right there is the black graph. Right there is the other red graph. Right here is the other red graph. Right here is the blue graph. You see what I'm saying? So that if you zoom in far enough, it doesn't matter what the graph is doing. If you know it's a tangent point, that point is on the graph, and you know what the slope is, then you can estimate where the graph is near that. Okay? So again, in calculus, think about limits, right? Limits are, okay, what's happening to the graph around a certain point? You can kind of tell that there's going to be a value in between because we're examining the limits, right? Well, now we're looking at a point. We're forgetting about everything else on the graph. We're looking at a single point, and I'm giving you the slope of the tangent, so you know the graph has got to be drawn a certain way. So we're going to actually be able to approximate values of an unknown function, or even a known function. I mean, most of these questions you're going to be given the function because you have to find the derivative of it. But we're not going to graph the function. We're going to approximate a value on that function. Okay? So we're going to use calculus to determine a point that is extremely close to another point that's on the actual function. Now, when I put it that way, it doesn't sound that exciting. But now I've given you this example. So think about this. Here is, and again, we're getting really close to the crux of this lesson here, okay? Here's the point slope form. Okay, y2 minus y1 equals m times x2 minus x1. So our x1, y1 is the tangent point of tangency, okay? Now x2 is a point that's going to be near x1. And of course, this is the question that comes up. Well, how close should I make it? Well, here's the thing. The closer you get to the point of tangency, the better the approximation will be. The further away you get, the worse the approximation will probably be. So the questions will say, find the value of a point that is, 15 100ths away. Okay, well that's pretty close, and you just do your best approximation. So if we have to choose a value, we're going to choose something that's close, right? But usually that distance will be given to you. So here's the second x value, and I am going to try and find a point on the tangent line. Okay, so again, here is the y value of the tangent line that is going to be an approximation of our actual function. The y1 value is going to, this is the point of tangency, okay? The x1, y1 is the point of tangency, okay? Can I just, maybe I'll draw this here. So the point of tangency here, Okay. Yeah. And what we can do is we can find the slope. Now this m, okay, is the slope of the line, right? And I'll talk about this again a little bit in a little bit. Like how do we find that slope? Well, it's the derivative of the original function evaluated at the point of tangency, right? But I'll talk about that a little bit more in a few minutes. All right, so now again, this x2 will be selected as well. And so notice what we have here. We have this piece right here is actually the run. It's the distance between the 2 points that are on the line, the run. And the slope here is rise over run. And so if this piece right here is rise over run times run, guess what? The runs will cancel out, and then all you have is the slight rise in y value. So get this is super cool. To find the second y value using this point slope form, or a variation of it, you take the original y value on the point of tangency and you can calculate the slight rise that gets to this next point. So I want to find out what that little bump is up. Okay, so that's what it gives us. All right, so here is, I'm going to give you now, this is the actual formula for a linear approximation, okay? Now, I was going to erase all this, but I think I'm going to leave some of it here, and I'll just walk you through it, okay? All right, so this first piece right here, L of x, okay, is this capital L is the linear approximation. So we are approximating a value on the function, but it's a linear approximation. So it comes from, it's actually a point on the tangent line that is a good approximation, okay? So the L of x, and again, this is the y value, right? The y2 value. Okay, we're approximating the y value on the function. And how we get that is we take the original y value of the point of tangency. So f of a. Now a is the letter that we often have used for the x value of the point of tangency, right? So this is the point of tangency y value. Because remember, this is what this looked like. Plus m times x 2 minus x1. Okay, so that's a plus. So this is what we came from, and this is what this is now. So this y value is f of a, the y value of the point of tangency. This f prime of a is our slope. So as I mentioned before, you do have to be given either the original function so that you can find the derivative, or you have to be given the derivative of the original function, or you have to be given the slope of the tangent line, which is what this is. So this is the slope of the tangent line at x equals a, right? F prime of a. So you got the y value of the point of tangency plus the slope at the point of tangency. And then you multiply that by the difference between x minus a. Now, this x value, okay, or let's just take this as a whole. This x minus a, remember, is the run here. So I'm going to rewrite this now as the run. So that's just the difference in x values. So a is your x value of point of tangency. This x is another x value that's just beyond or just before the point of tangency. So this is your second x value, and you will be given this, or this will be included, plugged into your equation. This will be the only unknown here, is the linear approximation. Okay, so this whole thing right here is delta x, or the difference in the x values. Okay, x minus a. That's the difference, the run. Any questions so far? No? Okay, so the y value, the bump, is the linear approximation. The original y value on the point of tangency is f of a. The slope is f prime of a, and this is evaluated at a. This has to be a number. This is not just an expression, it's a number. And then the run is the difference in the x values being considered. The point of tangency being 1, and the x is the slight bump in the horizontal direction. Okay, so L of x, this L of x, is the linearization of f of x. So this is terminology as well that you will see the linearization of f of x. So you can have an expression here or an actual value depending on if the x value is actually a number or not. So and I'll get into that later. Okay, so the L of x is also called the linearization of f of x. It represents the approximation of a value of f of x using a point on the tangent line near the value to be estimated. So for example, if the point of tangency, sorry, I thought I had some of this erased. If the point of tangency is right here, then we can tell that the linearization is going to be a very good approximation for a narrow range, right? And let's say that's like our 0.67 units or whatever, right? It looks like there. That range is not going to be the same for each graph, because you could have a graph that's very sharp like this, right? Like a parabola or something. And then that range where it's very good is very small, okay? But as you can see, and again, this is just visually, this is decent. Okay, that's good. We're starting to get, I'm going to zoom just a little bit in here for you. We're starting to deviate just a little bit too much. So this is good. This is so-so. It starts to deviate here, right? So-so. That's a technical term. So-so. Okay. Now this one, if you get too far away, obviously the curve is going to deviate from the straight line, right? It's a curve, it's not a straight line. We don't know what's going to do, but you're going to get bad. This is going to be horrible, right? That's a horrible approximation. But is it an approximation? Yes, it's just not a very good one, because the run that we've taken, the space away from the point of tangency is too far. Am I getting through? Is this pretty easy? I feel like I've said a lot of the same stuff over a few times, so hopefully you're getting it. So we've taken a look at this equation. There's a clean one right here, okay? Okay, and we're going to move now very quickly to an actual example where we're going to use this, all right? So we're coming. So here's the linearization equation. It represents the value near the estimate. Okay, yeah. Here's example one. Okay, so this is the type of example that you're going to see. They're going to say to you, without a calculator, okay, so no calculators here on the AP exam. This will be a no calculator section. So you can't just go square root of 4.26 equals. Here's the answer. Can't do that. You have to use your knowledge of calculus and your understanding of this formula to show a linear approximation of what? The square root of 4.26. Okay. So this question requires you to have a little bit more of a full understanding of what we're doing, because there's a few pieces that are missing. They're not giving you. Now, what aren't they giving you? Well, they're not giving you the equation of the function, okay? They're not giving you that. But they are telling you that what you're trying to approximate is the square root of 4.26, okay? So we're trying to approximate a square root of something. And so the original function, as you can tell, should show the square roots of x values, right? So my original function, f of x, is square root of x. And you can see that on the diagram here, on the graph here, this x, this red graph appears to be the square root. The square root of x equals 1 is 1. The square root of x equals 4 is 2, all right? Now, a good point of tangency is going to be a point that we know some values for that is near 4.26. So this is the other thing. If you have to choose a point of tangency, you're not going to choose the point of tangency 1, 1, right? Because even if you do find out what this slope of this line is, 4.26 is like over here somewhere. So this is going to be a horrible approximation. Do you see that? So the point of tangency that you pick, if you have to pick it, because sometimes they'll give it to you, but this is a good one because we have to assume some stuff. There's some stuff that we have to understand first. So I'm going to use the square root function as my f of x, and the point of tangency should not be 1, 1. I know that that's a point on there. It also shouldn't be 9, 3, right? Because that's way over here, and that's going to have an equally horrible tangent, right? Well, it's not going to be quite like that, but you know what I'm saying. Like, it's going to be bad, right? You don't want this. So what we want is a point near this that we know the values of, and that is the point 4, 2, right? So f of 4 is 2, okay? That's the point 4 comma 2. That is on the line, so this will be the point of tangency. Okay? Point of tangency. All right, so we have our function. I can take the derivative of this function pretty easily, right? I know what my f of a is. My f of a, now that's the point on the, that's the point of tangency, right? So f of a is going to be what, 4 or 2? 2, right? Because look at, there's the 2, the y value, okay? And my a value is going to be 4. Okay, so if we go back to here, I have this, I have this. This x, guess what? This x, 4.26. So I have that x as well. All I need to do is I need to find this yet. And then I just plug values in, okay? So f prime of x, let's just do that first, is going to be, let's use the power rule, and root x, of course, is the same as x to the 1/2, isn't it? So this is going to be 1/2 x to the negative 1/2, right? Drop this down, subtract 1, and so here we go. Now, I need to find f prime of 4. Very good. So I have 1/2 times 4 to the negative 1/2. Okay, so without a calculator, there's no calculator here. Obviously, this is 1/2, and this is 1 over square root 4, right? So that's 1/2 times 1/2. It's 1/2 times 1/2, which is 1/4. So does everyone see that the slope of this line here is 1/4? M. The slope is 1 over 4. You okay with that?
Yeah.
Awesome. So now we have all the pieces, and I can find out what this linear approximation is. Now, again, what we're trying to do, so let's take a look at this graph. This is 1, 2, 3, 4. So there's 5 squares in between each number. So 4.2 is exactly this line right here. So I'm looking for 4.26, which is going to be like right here somewhere. So I'm trying to approximate this value right here, which is super close to the point of tangency. And as you can tell just visually, it looks like it's going to be very, very close to the actual value, right? But I'm not using a calculator to find square root of 4.26, right? Okay, so let's give it a try here. I'm going to use red. So I'm going to use the linearization of, now this x value is 4.26, isn't it? That's my actual value. So what is the linear approximation of the square root of what? 4.26. That's going to be f of a, we said was 2 plus f prime of a is 1/4, good, times, this is going to be 4.26 minus 4. Oh, you guys are awesome. Okay, so the linearization of 4.26 is going to be 2 plus, this is 1/4 times 0.26?
Yes. Yeah.
Okay, going to be positive. Now this could be negative, right? If the slope is negative, right? Or if this point is in front of, right, we have to subtract. We have to go down if the point was in front. So this would be, these two would be flipped, let's say, and then you'd have a negative value here, right? We don't have that, but if you just follow the process, it'll all work out wherever your x value is. Okay, so, boy, can I, okay, so 4.26. So what's 1/4 times 0.26? Does 0.26 divide evenly by 4? Is 6 times, what's 6 times 4? 20, is that 26? That should be a hard question.
No.
Get your brains going. 6 times 4 is 24. Okay, so 26 doesn't divide evenly by 4, right? Okay. So you guys are like, I'm just wondering if you're awake here. So this is good. Okay. So if we didn't have a calculator, what should I do?
You can write the 0.26 over 4. Since it's a decimal, you have to multiply
okay.
numerator and denominator both by 100.
Okay, awesome. Okay, so let's just take this a little bit at a time here for sure. So you could, you said 0.26 over 4. Mm-hmm. And then because you don't want decimals in there, right? I mean, you could simplify this, I guess, to 0.13 over 2. That might be a good idea, right? Because half of 26 is 13, so 0.13 over 2. Yeah, you could do that. Now, I like the idea of let's have a fraction here. I mean, we could work with decimals, I guess, too. Could you Like a decimal is actually okay. So what's 0.13 divided by 2? Are we good enough to do that? 0.065? Yeah? Okay. Let's just see. 13, it would be 13 over 200. And then we could do it. Let's do a fraction, and then we'll do a decimal. So 2 plus, this is 13 over 200. Okay, and again, maybe we don't need to talk about all of this, but you're going to have to, do this without a calculator. So what do you do, right? Okay, so is that right, 13 to 200? So this is going to be, if I'm going to multiply top and bottom by 200, this is going to be 400 over 200 then? So this would be 413 over 200. Okay, could that be simplified any, do you think? Actually, don't worry about simplifying. This is fine if you're on the AP exam. You do not have to simplify. There's less simplification required in the AP exam. Okay, now that's our linearization. Let's see what the decimal. So we said that this as a decimal was 4.26. So 2 plus 0.065. Okay, so that would equal 2.065. Okay, so now let's just check. Where's my calculator? Okay, so double check with the calculator there. Then yes, we have our decimal is 2.065, and this 413 over 200 is the same. So either of those would work. You started with a decimal, so it would be totally fine to have a decimal in your answer. Generally, the general rule, I guess. Okay, so now here's the big reveal. Let's just see if the actual square root of 4.26. Let's see if it's close. Ready? Ooh, 2.06397 or 2.064. Hey, so we're only 1,000th off. Hey, it's not bad. Hey, a little more than 1,000th, I guess, but you get it, right? So see, that's a pretty good approximation, and we did not need the calculator at all for that. All right? So we did have to know a few things though, right? You have to figure out what the function is. So we need an original function. Well, it's a square root of 4.26, so let's use a square root function. That function will have x values and all of their square roots mapped on it, right? We have to find a point of tangency to set up here that's near the value we're trying to approximate. So we don't want to pick 1, 1, we don't want to pick 9, 3. We want to pick 4, 2, because that's really close to this value. Now, if I said approximate the value of 8.99, you would pick 9.3, right? Because that's really close to a value we know on there, which I just feel like I should make you do right now, just to see if you can get it. Let me see what my next example is. But and then you have to find the square root of said function. I'm sorry, the derivative of said function, and evaluate that at the point x value, the point of tangency, to get that slope, right? And then you simply plug it in to this bad boy right up there. Okay, on a scale of 0 to 5 of understanding, give me a little idea of where you're at with this, if you think you understand so far. Okay, fingers. Okay, lots of 4s and 5s. I love it. Okay, let me see what I have next here now. Ooh, oh yeah. Okay, so you're on. You're on. Example 2, without a calculator. This is just like the first one. I even given you the graph. I even give you the linearization equation there. Use linear approximation to determine the square root of 3.91. This is not 8.99. That would be a good one too. But 3.91. So go ahead, take a few minutes, look at the previous example we just did. I'll give you time right now to try and solve that, and then we will reconvene in a minute or two. All right, so there is the solution on the board there. So you're looking for the linearization of 3.91. And again, talking square roots, so we're going to use the function. The original function is root x. The point nearest to this one, right, the x value nearest to this one that we would know the y value of, and again, because that's important, is the 0.42, right? And so we're going to use this point, and the derivative is still the same because we're using the same point as the previous example. So here's your slope of the tangent line. Here's your y value. The difference between these two, now you got to be careful here. Remember, it's the x value minus the x value of the point of tangency. So this is a negative, right? So that's why we're going underneath here now. If this is the tangent line, we're actually we're going to go down, right? It's got to go less, so we're going down. So the fraction there, the rational, 791 over 400 is totally fine. And then if you can do this in your head without a calculator, so you think about 4 times what gives you 9? Well, that's 2.25. So two decimal places to the left, right, would be 0.0225. So if you can subtract that from 2, then you would get 9, and then this is 225 is 775. So you could do that as well, but I think this should be totally fine. All right. Yes?
Yeah.
Awesome. Now, let's see here. Okay. I'm going to go back to my teaching page here. I want to do one more example with you. We have about 10 minutes left, so I'm going to do one more example. This is not a square root function now. Same idea, different function. Okay? Different function. And it's going to give us a little bit more information here too. So example 3, find the linearization of f of x equals cos x. So it gives us the function that we're going to be using. And it also gives us the a value. So this is at x equals pi over 2. So the linearization, and this is our point of tangency, so this is a equals pi over 2. And use this information, the f of x and the a value, to calculate the cos of 1.75 without a calculator. So here's a legitimate, cos of 1.75 without a calculator. That's going to be nearly impossible, right? You would calculate it for that. But we're going to approximate it. So it seems like if we break it down into pieces, we're going to be able to determine these pieces without a calculator and then put them together for our approximation. So let's give this one a try. Okay, so our formula, L of x equals f of a plus f prime of a times x minus a. That's our linearization formula. Good to commit that to memory. We are given the a. Now I'm going to have to find the derivative of this function, right? So I need to find the derivative of the function, which is really easy. What's the derivative of cos? Very good. It's negative sine x. Okay. And I want to find the slope of this tangent at pi over 2. So f prime of pi over 2 is what we're going to need for this. And that's going to be negative sine of pi over 2. Hi.
In the previous question, didn't we put the point of tangency in the I think I'm confused.
We put the x value of the point of tangency into the tangent,
Yeah.
right?
Yeah.
Yeah. So we found the derivative. We found the derivative here.
Yeah.
Then we put the x value of the point. We put a. We put a into there. And that's what we're doing here, right? Okay. Is that a problem? Does that look different?
Yeah, can we continue?
Sorry?
So we can continue. I'm good.
Okay. Okay. All right. Didn't understand what you said. Negative. So what's negative sine of pi over 2? Negative 1? Okay. So pi over 2 is this one. So that's 0, 1. So the sign is 1, negative, negative 1. Awesome. Okay, so that's our slope. Okay. What about this f of a? Do I have that? Am I given that? No, I'm given a. I'm not given f of a. So f of pi over 2, that's going to be cos of pi over 2, right? So what's cos of pi over 2? 0. So it equals 0. Okay, so this was given, and this is me 0. And then 1.75 is going to be our x value. Okay. 1.75, and then we got pi over 2. That's interesting, hey? Okay, all right, well, we can do that without a calculator, hey? We can do that. So where are we at here now? Okay, so we've got that figured out. I've got this figured out here. So let's start filling stuff in. I'll use yellow. Can you guys see yellow okay?
Yeah, that's okay.
Is that okay? Okay, so the linearization of, oh shoot, I messed up already. Pi over 2, right? No, 1.75. 1.75 goes there. F of A we said was 0. F prime of A is -1. And x minus A is going to be 1.75 minus pi over 2. Okay. I don't like yellow. You guys might like it. I don't like it. Looks good up there? Okay, it doesn't look good on my screen, so all right, so let's keep going here. 1.75 is going to be 0 minus 1 times. Now, I can get a common denominator, I guess, here, right? What's 1.75 times 2? Is 2 3.5? Okay, 3.5 minus pi over 2. 3.5 pi, oops, 3.5 over 2 minus pi over 2. Okay, L 1.75. So this is going to be negative. What's 3.5 over 2? Or actually, let's do this. Let's do 3.5 minus pi. Let's do 20 and 35. Let's get rid of the decimals there and then make this a 20 and make this a 10 pi. What do you say? Okay, so this is going to be negative, let me just, one step at a time. So 35 minus 10 pi over 20. So positive 10 pi minus 35 over 20. Okay, or you could do, pi over 2 minus 35 over 20, I guess. Okay, we need to check that now. Okay, so that appears to be the correct answer. Now let's just see what we would get if we did actual cos of 1.75. We might have to find this out as a decimal to compare, but are we in radians? Yep. So cos of 1.75, negative 0.1782. What is this as a decimal?
Negative
0.1792.
There's a 0 in front of there? Or just 0.17?
0.17.
Negative 0.17 what? 92? Okay, so it's pretty close. Okay, so this is negative 0.1792, negative 0.1792. Okay. Yeah, and then that's pretty close to our actual calculation over there. Okay. So is everyone kind of seeing what's transpiring here?
Yeah.
Okay. Trying to get. Oh my, what's going on? I'm trying to do a screen clipping here. I'm on freeform. Freeform. Okay. Going freeform clipping. Okay. So see that pretty close. Pretty close. Got it?
Got it.
Yep.
Awesome. All right.
Oh.
Here is your signalement.
What?
You're a signalement.
Oh.
That's how they said it in ancient Greece,
Yeah.
I think.
I don't believe you.
We say it assignment. But I don't like leaving letters out. Like, why are they silent? Like,
You should be
they need to be seen and heard. A signalement.
Yeah.
You've never heard me say that before?
Never.
I've said that before. You've been a student of mine for years. Come on. You haven't heard that before?
4 years.
A signalement. A signalement.
Oh, you're not. That's
All right, there you go, Finny.
good.